All right, let's get going here. You all have a midterm on Monday? Yep. All right. I'll see what I can come up with before then. That just looks great. All right. Today is the 5th. So last time we had talked about the dot product and stuff. We just gotten talking about projections. So let's briefly talk about projections, then we'll talk about matrices, because that's kind of where you guys are at right now, right? Talked about matrices yesterday and kind of most of the things you do with matrices as far as like the operations, which are not too terrible. We'll get to them in a minute, but let's talk about projections for a minute. So projections. Let me move this table a little bit here. Projections. The calculation is relatively easy, but it's good to know where it comes from. So here's the idea. When you're finding projection, you've got essentially two vectors, A and B, and there's some angle between them. And the idea is that you're essentially just dropping one vector down onto the other. You're doing a perpendicular, oh gosh, the word. We're dropping a perpendicular. So this vector here that I'm drawing, that vector is the projection of B onto A, which we usually write as PROJ, a subscript A, and then the vector B. So the vector that's getting projected onto is the one that looks like it's lower in the notation. This is the projection of B onto A. That's why B looks like it's above A. And the way we're going to find this projection is by finding first its length, then its direction. Because that's all you need for a vector, is a length and a direction. To find the length, which I do not love the notation here, but the length we call the component of B onto A. So the length or magnitude of the projection of B onto A is called, it's written, I should say, it's called the component of B onto A, which again, I do not love this choice of name, but it is what it is. And is written as, with the same sort of notation, it's COMP B onto A. So that's what we're going to find first, just the length. And to find the length, we're just going to use some trigonometry. We're going to say the cosine of this angle, the cosine of the angle theta is equal to the adjacent over the hypotenuse, which is going to be the thing we're trying to find, the component of B onto A, divided by the hypotenuse, which is the length of B, or the magnitude of B. Good rule of thumb with vectors, if you see a cosine, it means you're probably going to use the dot product eventually. So here's what we're going to do. We're going to multiply both sides by the things we need so that the dot product shows up. So reminder, so just as a reminder over here, A dot B is equal to the magnitude of A times the magnitude of B times cosine of the angle between them. So here's what we're going to do to make this magical thing show up. We're going to multiply both sides of this equation by the magnitude of A times the magnitude of B. So we're going to have on the left-hand side, the magnitude of A times the magnitude of B times cosine of theta equal to the magnitude of A times the magnitude of B times the component of B onto A divided by the magnitude of B. The magnitudes of B on the right-hand side cancel. And we're going to rewrite this as, well, the left-hand side is A dot B. So the A dotted with B is equal to the magnitude of A multiplied by the component of B onto A. And finally, solving for this, we get A dotted with B divided by the magnitude of A is equal to the component of B onto A. Or another way of saying that is how long the projection is, or the magnitude of the projection. The rest of it's easy. Now that we know the length, we haven't actually really talked about this, right? So actually, I'm going to save this here. I'm going to come. I feel like there's something I should say as an example before we do this. So one example, real quick, off to the side here. Sorry, I just thought of something that seemed worthwhile. So here's something I want to point out. We want to find a vector in the same direction as, sure, 3, 2 with a magnitude of 7. I know this feels like it might be unrelated, but it's definitely related. So how do you find a vector in a certain direction with a certain magnitude? Well, you find a vector of length 1, or the unit vector in that direction, and then you multiply it by the length you want it to be. So the unit vector in that direction, and let's go ahead and call this vector V, is going to be the vector V divided by its own magnitude, which in this case is going to be the vector 3, 2 divided by the magnitude of that, which is the square root of 3 squared plus 2 squared. So our unit vector is 1 over the square root of 13 times the vector 3, 2. And then the vector we're actually looking for is that vector multiplied by 7. So the vector we want is 7 multiplied by this unit vector that we just found, which is 7 over root 13 times the vector 3, 2. We'll off to the right here, sorry. So that's the idea. If you're ever trying to find a vector and you're describing it as a length and a direction, you simply take the length of the vector and multiply it by the unit vector that's in the correct direction. Let me ask everybody a question. Do we know this vector actually has the right length? Let's check it out. Let's go ahead and find, so actually let's distribute this, even though I don't love distributing this. Let's write it as 21 over root 13, 14 over root 13. Good question. 7 is probably a larger number than I should have picked. Oh well, such is life. So the magnitude of this vector, so the magnitude is going to equal the square root of 21 over the square root of 13 squared plus 14 over the square root of 13 squared. 21 squared is 441. 14 squared is 196 divided by 13. And hopefully this works out all right. Let's see. I feel like it's not going to work out all right, but who knows? So we have the square root of, let's see, 637. That seems totally not great. But 637 divided by 13 is, I think it's 49. I'm pretty sure it's 49 because 13 times 50 is 650. 13 times 49 is 1 less 13, which is 637. So yeah, that's the square root of 49, which, hey, that's 7. It checks out. Cool. So it is definitely true that when you multiply a unit vector, or really a vector of any length, by whatever length you want to multiply it by, you end up with a vector with the corresponding length multiplied together. So cool. What that means for us back here is that if I want to find the projection vector, all I have to do is take the length of the vector I have and multiply it by the appropriate unit vector in the right direction. The direction being the direction of A. So my unit vector is going to be A divided by the magnitude of A, and my projection of B onto A is going to equal the length A dot B divided by the magnitude of B. Sorry, the magnitude of A, apologies. I said the wrong thing or wrote the wrong thing. Multiplied by the vector A divided by its own magnitude. This is our length, our magnitude. This is our direction. And then I'll point out, most people usually write this as A dot B divided by the magnitude of A squared, all multiplied by the vector A. Or some people, me mostly, like to write it as A dot B divided by A dot A, all times the magnitude of the vector A. But that's your projection formula. It's probably something you should memorize, unless he says you don't need to. Yeah, sorry. I know I went a little bit quickly there. Sorry, there's lots of things to see here. Let's see if I can change it. I feel like I'm in my own way here. Apologies. Yes. So the direction, I would say the direction vector is the vector A divided by its own magnitude. Because the projection of B onto A points in the direction of A. So what I usually remember about these projection formulas is the vector you're projecting onto is the one that's showing up like most of the time. Like for B onto A, it's A everywhere except for one little B right there. Everything else is A. That's how I kind of think of it. A is the important thing, B is just what we're projecting.
The cosine left because with A together.
Right, because this whole thing right here, sorry, this whole thing right here is A dot B. So we rewrote it in the easier way to express it. Because we don't usually know the angle between the two vectors. Let's look at an example with some actual real numbers. So let's say we have the vector A equal to 4, 3, and B equal to 1, 4. Let's go ahead and draw it. Here's A. B. And I'm going to drop a perpendicular from B onto A. And we're going to find the projection. So, and let's, yeah, no, I don't like doing it. So let's find the projection of B onto A. So projection of B onto A. I'm just going to start off by writing it's A dot B divided by the magnitude of A squared, all that times the vector A. All right, we can do this. A dot B is going to be 4 times 1 plus 3 times 4. The magnitude of A is going to be the square root of 4 squared plus 3 squared, all that squared. You might notice here why someone like me would prefer to say that the bottom part is A dot A, so I don't have to think about having a square root there. A dot A would just be 4 times 4 plus 3 times 3, which is going to be the same thing. Either way. And then multiply by the vector A, 4, 3. So multiplying this out, let's see, 4 plus 16 is 20. Sorry, 4 plus 12 is 16, apologize. Divided by the square root of 5, the square root of 25 squared is 25. All times the vector 4 comma 3. I don't feel like distributing this is super helpful, but we can. We get 48. Sorry, gosh, my brain not working super hot today. 4 times 16 is 64 over 25, comma 3 times 16 is 48 over 25. So it looks like we've gone over about 2.5 and up about 2. That seems reasonable. Consider our picture. Right? It looks like we got over a little more than 2, up almost 2. Yeah, not bad. Another thing people ask about or talk about here is the orthogonal complement. So the orthogonal complement written as ORTH of B onto A is the vector you would have to add to get back B. So here's the idea. The projection of B onto A plus the orthogonal complement of B onto A should add up to B. So if you know the projection and you know B, you can subtract the projection to find the orthogonal complement. So the orthogonal complement of B onto A is B minus the projection of B onto A. In this particular case, it's going to be B, which is 1 comma 4 minus our projection, which is 64 over 25 comma 48 over 25. Doing the subtraction, 1, which is 25 over 25, minus 64 over 25 is going to be negative 39 over 25. And 4, which is 100 over 25, minus 48 over 25 is 52. The vector we're talking about is this vector right here. That's your orthogonal complement of B onto A. There's your projection. B. And the projection plus the orthogonal complement gives you the vector B. This orthogonal thing isn't super duper important, but it is this is the moment to talk about it. Yeah. There's not a whole lot else to say there. So projection is a relatively straightforward calculation. Probably should memorize the formula. I guess I should ask, are there questions about this? That is a 39, yes. Because I have, right, this is 25 over 25, comma, 100 over 25, minus 64 over 25, comma, 48 over 25. And assuming I've done my arithmetic correctly, I think 24 minus 65 is negative 39. I think. Yeah, that sounds right. Other questions? Yeah. Fair question. What is the component? So for this question, the component, right? Component's the right word. I never remember the right word for that. Component seems like the right word. Of B onto A is the magnitude of the projection. Let's just calculate it as B dot A divided by the magnitude of A. So B dot A again is 16. And the magnitude of A was 5. So that's your component of B onto A. That's the length of your projection vector. Yeah.
So like on the graph,
Well, so I wouldn't really label it on the graph because I don't typically like to label the length. I like to label the vectors. So I want to point out this thing here, not a vector. Right? It's the length of that vector. Although I will say typically with things like with triangles, you usually label their lengths, not their vectors. So okay, fine. Like this, so right here, right, this length would be 16 over 5. There's your component length. trying to think what else to say about this. Yeah, projections. I think that's it. Oh yeah,
Projection, A onto B would be just B.
good question. So I was hoping someone would ask that. So to switch it around, the projection of A onto B, let's draw it again. So 1, 2, 3, 4. 4. Here's my vector B. A was 4, 3. Yeah. A. And so if this vector here wasn't long enough, you could extend it. I think it might be long enough, but I think it's like a close call here. So if I drop a perpendicular from here to here, it looks like it's maybe like right about there, but who knows actually, because my picture right might not be perfect. So this vector here that we're going to find, that's your projection of A onto B. Which looks like it's almost as much as B, but we'll see. So same calculation. This is where I like to point out the thing I said before, which is the projection, the whatever vector you're projecting onto, in this case B, is the one that's showing up most of the time in your calculation. So for the projection of A onto B, it's going to be still the dot product, but then we're dividing by the magnitude of B squared multiplied by the vector B. Whatever you're projecting onto is doing the majority of the work in our calculation. The vector that's getting projected is only showing up once. So in this case, the dot product still is the same. It's still going to be 16. Let me write down my vectors here just so everybody remembers them. A is the vector 4, 3. B is the vector 1, 4. And then my magnitude of B is the square root of 1 squared plus 4 squared. And then we're multiplying by the vector B, which is 1, 4. So it looks like it's going to be just slightly smaller than the vector B. Yeah, slightly smaller. Yes, sure. I think now I feel like I'm saying something kind of funky. I feel like I'm making a mistake somewhere here, but that's okay. So I have 16 divided by the square root of 17 times the vector 1, 4. I feel like I'm making, oh, I forgot to square the denominator. That's the mistake. I'm like, something feels wrong here. This is why I don't like writing it this way. I should be squaring that. Apologies. I'm like, that seems weird. There we go. So that's 16 over 17 times 1, 4, which is just a little bit less than the vector 1, 4. So our picture looks reasonably appropriate. And if we want to know the component of A onto B, even though you could find it as just the magnitude of this vector, I really think it's easier just to go back to the original formula and say, yeah, it's going to be A dot B divided by the magnitude of B, which is going to be 16 divided by the square root of 17. We're not done with vectors, but we're moving on to matrices. But really, when we talk about matrices, there's a lot of vectors that still are going to come up. How many of you are taking 17C next quarter? Okay, so all this matrix stuff we're about to talk about is well, not all of it. A lot of this matrix stuff we're going to talk about is going to show up next quarter. Specifically, the things for 2x2 matrices. The other stuff we're going to talk about, it's not super duper important, except that you have to know it for your midterm and or final. But other than that, it's really just the 2x2 matrix stuff that's going to carry it forward to 17C. So let's talk about some matrices. Matrix algebra. So let's start with the following. We've got a couple matrices here. A is a 2x2 matrix with components 2, 1, -3, 5, or entries 2, 1, -3, 5. B is the 2x2 matrix 4, 0, 1, 3. And C is the 2x3 matrix 6, 1, 2, -1, 0, 1. And D is the 3x2 matrix 1, 2, 3, 4, 5, 6. So many of the matrix things we do are going to work how you would imagine they would. Adding matrices, subtracting matrices, multiplying a matrix by a scalar, all those kind of work how you might imagine they would. So for example, if I wanted to find A plus B, it would be, well, I'd get 2, 1, negative 3, 5, plus 4, 0, 1, 3. And then you, just like with vector addition, you would add the corresponding components together. So you'd get 6, 1, negative 2. Same is true for subtract. Now, I will say, one thing that has to be true about matrices that, well, it also has to be true for vectors is you can't add matrices together that aren't the same size or subtract them. So if I said, what's A plus C isn't defined. Because there's a size mismatch. Right, A is a 2 by 2 matrix, C is a 2 by 3 matrix. They aren't the same size. We can't have them together because we're missing components from one part. The other thing I'll point out here is if we have scalar multiplication. So for example, if I had 4 times A minus B, so that's 4 times 2, 1, negative 3, 5, minus 4, 0, 1, 3. This 4 just multiplies each component of the matrix A. So we can write this as 8, 4, negative 12, 20, minus 4, 0, 1, 3, and then subtract. 8 minus 4 is 4. 4 minus 0 is 4. Negative 12 minus 1 is negative 13. And 20 minus 3 is 17. So matrix addition, matrix subtraction, and scalar multiplication all kind of work in a normalish way. The only kind of caveat is that the matrices have to be of the same size to be added or subtracted together. Now, on the other hand, matrix multiplication is a whole different animal. So let's look at an example. Let's calculate A times B. So, okay, so A times B is going to be the matrix 2, 1, negative 3, 5 times the matrix 4, 0, 1, 3. I know we said it in class, but we'll say it again here. When you multiply matrices together, you're always going to take rows of the first matrix or the left matrix, columns of the right matrix, and you're going to take their dot product. So it's kind of like you're imagining each row of the matrix is a vector, and each column of this matrix is a vector, and you're going to do the dot product of this vector with that vector. So when we write this out, and then normally I would probably skip writing all of this arithmetic. I'll write it here. For our first entry, we're going to get 2 times 4 plus 1 times 1. The first row dotted with the first column. Also worth mentioning, when you dot the first row with the first column, your result ends up in the first row and first column of your resulting matrix. That is not a coincidence. Now, if I do the first row dotted with the second column, I get 2 times 0 plus 1 times 3, and my result ends up in the first row and second column. Again, not a coincidence. Now, and here's how this process usually works. You take your first row of your left matrix and you just keep throwing it at all the columns of your second matrix until you've exhausted them. And then you move on to the next row of your first matrix and repeat the process. So I've exhausted the columns in the second matrix with my first row here. So now I'm going to move down to my second row and do the same thing. Second row dotted with my first column is going to be negative 3 times 4 plus 5 times 1. Second row dotted with my second column is going to be negative 3 times 0 plus 5 times 3. And then we simplify. See, we get 8 plus 1, we get 0 plus 3, we get negative 12 plus 5, and we get 0 plus 15. So that's the matrix A times B. Let's see what happens if we multiply them in the opposite order. So do B times A. Usually you don't write like a multiplication symbol between them. You just write the matrices next to each other. B times A is just B next to A. So that's going to be 4, 0, 1, 3 multiplied by 2, 1, negative 3, 5, which is going to give us. So normally I wouldn't write out all these arithmetic here. I would just do the math mentally. So 4, 0 dotted with 2, negative 3 is going to be, I like to point at things here. It's going to be 8 plus 0. 4, 0 dotted with 1, 5 is going to be 4 plus 0. 1, 3 dotted with 2, negative 3 is going to be 2 plus negative 9, which is negative 7. And 1, 3 dotted with 1, 5 is going to be 1 plus 15, which is 16. Very, very, very important to observe. This is not equal to A times B. And this is probably one of the first instances you've noticed or seen where an operation is not commutative. Actually, that's not true. You know non-commutative operations totally. Subtraction isn't commutative, right? 3 minus 5 definitely doesn't equal 5 minus 3. But this is a kind of a more interesting situation where multiplication, the order actually does matter, unlike with regular numbers. So for matrix multiplication, you have to be extra careful. Make sure you're multiplying things in the correct order because order really does matter. So matrices don't have to be the same size to get multiplied together, though. For example, we totally could multiply D times A. D is a 3 by 2 matrix. 1, 2, 3, 4, 5, 6. A is a 2 by 2 matrix. 2, 1, negative 3, 5. And the dimensions match in the right way. Because when you do a row of the first matrix with a column of the second matrix, there's the same number of entries. My rows have 2 entries, my columns have 2 entries, so that's gonna work. Another way of saying this is that D is a 3 by 2 matrix, A is a 2 by 2 matrix, and the inner dimensions match. That's the requirement for matrix multiplication to be defined, is that the inner dimensions of the 2 matrices have to match, meaning the number of columns in the first matrix have to match the number of rows in the second matrix. And then we just do it. So we get, let's see here, 1, 2 dotted with, oops, I made matrix too small, that's fine. So 1, 2 dotted with 2, negative 3 is going to be 2 plus negative 6, which is negative 4. 1, 2 dotted with 1, 5 is going to be 1 plus 10, which is 11. Move on to the next row. 3, 4 dotted with 2, negative 3 is going to be 6 minus 12, which is negative 6. 3, 4 dotted with 1, 5 is going to be 3 plus 20, which is 23. 5, 6 dotted with 2, negative 3 is going to be 10 minus 18, which is negative 8. And 5, 6 dotted with 1, 5 is going to be 5 plus 30, which is 35. On the other hand, A times D is not defined. You try to write it out. A is 2, 1, negative 3, 5. D is 1, 2, 3, 4, 5, 6. We cannot dot the rows of A with the columns of B because there's a mismatch in the number of elements. The rows of A have 2 entries, the columns of D have 3 entries. We can't dot those things together. They have to have the same number of entries. Or writing it out in the other way, A is 2 by 2, D is 3 by 2, and the inner, right, literally just taking the inside dimensions, right, the inner one there, the inner one there, the ones that are in the inner part of this multiplication, those don't match. Not a match. So we can't do the multiplication. Okay. It's good to practice this. So you all should try calculating Sure, let's do C times D. Yeah, let's do C times D, which is going to be the matrix C, which I'll write out for you is 6, 1, 2, negative 1, 0, 1, multiplied by 1, 2, 3, 4, 5, 6. Everybody calculate this. Oh, actually, I'll say one more thing before I actually calculate this. C is a 2 by 3. D is a 3 by 2. The inner dimensions match. And the resulting matrix is going to be what size? 2 by 2, because the resulting matrix is going to have the dimensions of the outer dimensions. So the inner dimensions have to match, and the outer dimensions are the size of your resulting product. So go ahead and multiply this out. Oof. Here's how things should be looking. It should be first row dot of the first column, which is going to be 6 plus 3 plus 10, which is going to be 19. And then first row, second column, 12 plus 4 plus 12, which is 28. Second row, first column, negative 1 plus 0 plus 5. And finally, second row, second column, negative 2 plus 0 plus 6. Those are resulting matrix, 19, 28, 4. Again, I will say, because I think he did kind of mention it, that your resulting matrix, the way you get a particular entry in a certain row and column is by multiplying that row of the first matrix dotted with that column of the second matrix. So I'll write this down more generally. So if we're saying that for any matrices A and B, if A times B is equal to C, then the ith row and jth column, that's not the way I will say it, sorry. Then the, apologies, then the entry in the ith row and jth column of C, typically written as Cij, is obtained by dotting the ith row of A with the jth column of B. Or in other words, Cij is equal to row I of A dotted with column J of B. Sorry, I keep tracking off to the right here. Sorry, just like, so that's not super duper important to like know that. I feel like it's just, I saw him mention that in class. It seems like it's worth noting. I think it's just neat to observe, kind of, but probably not that important. Maybe, I don't know, maybe it will be. You never know with the Dell. It's always a who knows. For clarification, the midterm you have on Monday, did he say through what section it's going to cover? Okay. Why would you know? Yeah. Right. So let's see. So looking at the homework, it looks like it's going to be up through section 8.6. Okay. Well then. All right. Continuing on. I feel like did he talk about transpose matrices? Okay, well, we'll talk about it. It's really easy. It's not terrible, but I was watching the videos. I didn't see him talk about it, but I thought I just missed it. So a transpose is super duper straightforward. What's that he did? Okay, all right. So just to make sure everyone's on the same page, if your matrix C is, so I'm still using the same matrices from before, which I forgot what they are. If C is equal to 6, 1, 2, negative 1, 0, 1, then the transpose matrix, which is usually written as a superscript capital T, although some people use a prime notation. So you could write it as C prime, although it's less typical. That's going to be equal to basically every row becomes a column, every column becomes a row. So the first row, you're now going to write as the first column. The second row, you're now going to write as the second column. Or if you prefer, you can think of it as your first column, you're now going to write as your first row. Your second column now is your second row. Your third column now is your third row. Rows become columns, columns become rows. That's kind of it. Like that's the transpose. There you go. Yes, we do use it. I'm trying to think, do we use it much? I mean, it's useful in matrix algebra. It might not be super useful in this or class or the next class, but it is like we're kind of just, this is kind of like we're covering our bases here. Like we're doing all the things, even though some of them might not be super necessary for this class in particular. If someone is like, have you seen matrix algebra? Like, yes, like, cool. Then you saw these things I would expect you to see. So we're kind of just building the foundation. Something kind of interesting is you can always multiply a matrix by its transpose in either order. So C transpose times C would be 6.2. I should say, usually we read them rows as rows, not small. So I really shouldn't say 6, 1, 2, negative 1, 0, 1. I should really say 6, negative 1, 1, 0, 2, 1. And then we're going to multiply that by 6, 1, 2, negative 1, 0, 1. So we're going to get, let's see what we get here. So we're going to get 36 plus 1, 6 plus 0, 12 minus 1, and then 6 plus 0, 1 plus 0, 2 plus 0, and then 12 plus negative 1, 2 plus 0, 4 plus 1. Somewhat interestingly, this matrix, this result here is called symmetric. I don't know if we really know that, but I just want to point out that this matrix is symmetric because it is equal to its own transpose. So if we call this resulting matrix E, I would just note that E is equal to E transpose. If you interchange the rows and columns of this matrix, you still have the same matrix. We can also do the multiplication in the opposite order. C multiplied by C transpose is going to be this 6, 1, 2, negative 1, 0, 1, multiplied by 6, negative 1, 1, 0, 2, 1. Multiplying this out, we're going to get a much smaller matrix. It's going to be 2 by 2, not 3 by 3. We're going to get, let's see, 36 plus 1 plus 4 is 41. And then negative 6 plus 0 plus 2 is negative 4. And then negative 6 plus 0 plus 2 is negative 4. And then 1 plus 0 plus 1 is 2. That matrix is also symmetric. It's also equal to its own transpose. All right, that feels like enough multiplying matrices. Sure, let's talk about a few other matrix things. So. Yeah. Trying to think of all the things I want to say here. Yeah, sure. So for any square matrix, when I say square, what do I mean? I mean a matrix with the same number of columns and rows. So a 2 by 2, a 3 by 3, a 4 by 4, et cetera, et cetera, et cetera. We can define a couple things. One, the trace of any square matrix is the sum of the diagonal entries. What are the diagonal entries? Those are the entries that appear on the main diagonal, which starts at the upper left corner and ends at the lower right corner. Alternatively, you could think of it as all the entries where the row number and the column number are the same. So the entry in the first row, first column, plus the entry in the second row, second column, and so on and so on and so on. So for example, if your matrix is a 2 by 2 matrix like A, B, C, D, then the trace of A, which is often written like that, is equal to A plus D. More generally, if A is a larger, say like A is an n by n matrix, which we would write. So here's how you write a general n by n. It's kind of annoying, but I'm gonna do it anyway. It's A11, A12, dot, 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 A1n. And then the second row is A21, A22, dot, 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 AN, A2n. And then we get down to the last row, which is the nth row, AN1, AN2, dot, 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 all the way down to ANN. The trace of this matrix would be A11 plus A22 plus A33 all the way to the last ANN. So for a trace of a matrix, I'm pretty sure something he didn't talk about in class, with good reason, is just something you get by adding up all the diagonal entries. Nice. This comes up more in the next quarter. But when I say more, I mean like a tiny, tiny bit. Like there's a place where it comes up and it is important. So it's nice to have just known, oh yeah, you just find the trace of a matrix by adding diagonals. So for example, if A is equal to 1, 3, 7, 8, the trace of A is 1 plus 8, which is 9. We don't define a trace for non-square matrices. Yeah, let's talk about that. We can also define the determinant of a square matrix. I don't want to make this more trouble than it needs to be. So here's what we'll say. For any size matrix, you can calculate the determinant, but it gets harder the larger the matrix gets. For small enough matrices, specifically 2 by 2 and 3 by 3 matrices, there is a convenient formula we'll talk about. So if A is a 2 by 2 matrix, A, B, C, D, the determinant of A is equal to the product of the diagonals, A times D, minus the product of the off diagonals, B times C. For a 3 by 3 matrix, A, B, C, D, E, F, G, H, I. There is a convenient way of finding the determinant there, although you may or may not be asked to do this. So the way you calculate the determinant of A is the following. You take either the first two columns and write them again next to the matrix, or the first two rows and write them below. I prefer to use the columns, as most people do. So over here, next to the matrix, I'm going to write the column A, D, G, and B, E, F, H. Good God, can I see the letters correctly? Maybe. And then here's what we do. We take the product of these things, A times E times I, B times F times G, C times D times H. So here, the determinant of A is going to equal A times E times I plus B times F times G plus C times D times H. It's like, is that a horn or a bird? Minus the product of the diagonals in the other direction. C times E times G, A times F times H, B times D times I. You do not need to memorize this formula. You just need to maybe know the process. And then for larger matrices, it just gets terrible. If he talks about determinants of larger matrices, let me know and we will talk about how you approach that. So for example, if A was equal to the matrix, again, 1, 3, 7, 8. It really sounds like a car alarm, kind of. Maybe it might be mimicking it. That birds do that. They hear noises and they make the same kind of noise. So, yeah, I'm gonna make a car alarm sound. Okay, determinant of A here would be 1 times 8 minus 3 times 7, which is 8 minus 21, which is negative 13. Or for a larger matrix, let's call it B. B equal to 3, 4, 0, 1, 2, 5, 0, 7, 1. The way you find the determinant of B, well, again, you're going to write down the same two columns. I'm going to write down a 3, 1, 0, and a 4, 2, 7. And the determinant of B is going to equal 3 times 2 times 1. I do think drawing the lines is helpful. So 3 times 2 times 1 plus 4 times 5 times 0. Don't write 4 times 5 times 0. Write 0. Or don't even write 0. Right? But don't write 4 times 5 times 0, please. And 0 times 1 times 7. Oh, also 0. Cool. Minus 0 times 2 times 0. 3 times 5 times 7. Okay, I actually have to write that. 3 times 5 times 7 plus 4 times 1 times 1. Don't write 4 times 1 times 1. If the multiplication is times the 0 or times the 1, come on, don't write more than you need to write. And so here we're going to get, let's see, 6 minus 3 times 5 times 7 is 105 minus 105 plus 4. So 6 minus 109 is negative 103. So that's how we calculate determinants of matrices. They're 2 by 2 or 3 by 3. Kind of neat. A couple other important concepts when it comes to matrices. Identity matrices. I'll actually talk about two things here. So identity matrices. So when you think of an identity matrix, what you're thinking of really is kind of like the number 1. In that when you multiply something by the number 1, you get the same something back. The identity matrix plays the same kind of role for matrices. So the 2 by 2 identity matrix is 1, 0, 0, 1. The 3 by 3 identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1, etc., etc., etc. So any size identity matrix is always square. So always square. We have 1s on the diagonal, 0s everywhere else. And just so maybe make sure everyone's clear, the main diagonal again is just all the entries where the row and column number are the same, right? First row, first column, second row, second column, third row, third column. That's your main diagonal. Or it's also just called the diagonal. Same deal here, right? Main diagonal is just those two entries right there. So you're starting in the upper left corner, ending in the lower right corner. Again, only for a square matrix. We don't really talk about them for matrices that have different numbers of rows and columns. What does the identity matrix do? Well, when you multiply by it, it doesn't change anything. So for example, the 2 by 2 identity matrix multiplied by a matrix A actually does give us multiplication in either order we're still working out. It's going to equal the matrix A. Let's look at an example. Let's say we have a matrix which is 5, 4, -3, 1. If you multiply that by the matrix 1, 0, 0, 1, look what happens. Let's see, you get 5 times 1 plus 4 times 0. That's 5. 5 times 0 plus 4 times 1. That's 4. -3 times 1 plus 1 times 0. That's -3. -3 times 0 plus 1 times 1. That's 1. Oh, look, we got back the matrix A. And it doesn't matter if you do it this way or this way. Yeah, so oh my gosh, identity matrices. Always square, ones on the diagonal, zeros elsewhere. Yeah, sorry, I know my penmanship is, as the quarter goes on, it feels like it just gets worse and worse and worse. So I would point out that although we call this the identity matrix, there really is another word there that we aren't saying that I would want to say. It's the multiplicative identity, which is just the thing that if you multiply it by something, it doesn't change to something. In real numbers, that number is 1. In real numbers, there's also an additive identity. The number is 0. If you add 0 to any number, you get that number back. In matrices, there's also an additive identity. It's the 0 matrix. In fact, there are additive identities of any size. You can have a 2 by 3 identity, additive identity matrix. So, for example, just as a note here, the 0 matrix of appropriate size is the additive identity. It's not super exciting, but if you take a matrix like 1, 2, 3, 4, 5, 6, and you add it to the 0 matrix of the right size, you're going to get back the same matrix you started with. Again, not super duper important, but something that people are just going to kind of expect that you've already seen. Right? Someone's going to say, oh yeah, we add 0, and you'll be like, well, huh? Right? This is what they mean when we add a 0 matrix. You're just adding the matrix full of zeros, but that is whatever size you need it to be to add it to the matrix you've got. I will point out this is more of a concept that plays a role in linear algebra, which most of you probably aren't ever going to take, but you might. There is a linear algebra for the 17 series. I think it's like Math 27A, I think, but I don't think many people are required to take it, so I wouldn't study too much. Sure. I feel like the Dell would ask this question. I should say the identity matrix definitely the multiplicative identity matrix definitely plays a role in 17C. You're going to see it a fair amount, so we definitely should remember what it is. Yeah, let's look at this question. I feel like even though I don't really want to do this next one, I feel like it's something that Dell would ask. So the next question is, show that for any 2 by 2 matrices, sorry, we have two of them, that A times B transpose, excuse me, is equal to B transpose times A transpose. Okay, so here's the deal, and this is why I wanted to point this out. You can't just pick any two matrices you want. This is generally true. If you're trying to show something is true for any matrices, you have to pick general ones. Meaning, we're going to say, well, cool, we're going to let A equal a generic matrix where we haven't specified any numbers. I like to call it A, B, C, D. And similarly, B, we're going to call it E, F, G, H. And then we're just going to calculate both sides, and hopefully we'll get the same thing either way. That's what, when you're trying to show things through, that's what you do. You calculate each one, and hopefully it works out. So let's do B transpose. Let's do the right-hand side first. So the right-hand side, B transpose multiplied by A transpose is going to be, let's see, B transpose, again, I'm interchanging the rows and columns. So B transpose is going to be the row EG and the row FH multiplied by A transpose, which is going to have rows AC and BD. Right, I'm taking my rows and columns and interchanging them. My B transpose, there's my A transpose. Okay, we're going to multiply it out. It's going to be a little bit gnarly. So it's going to be E times A plus G times B. And then it's going to be E times C plus G times D. When you're multiplying these out, make sure that you give yourself enough space between the entries here and here so that you're not confusing what's in the first row, first column, what's in the first row, second column. There shouldn't be any commas though. Like you have to leave yourself enough space, which is kind of annoying, but it's the way it's written. Let's see, second row, first column, F times A plus H times B. Finally, second row, second column, F times C plus H times D. All right, let's go ahead and calculate the other thing, A times B transpose. So A times B transpose, well, let's see, it's going to be A times B. So we have to do the insides first. So A is A, B, C, D. B is E, F, G, H. And after we multiply those together, then we're going to take the transpose of that. So multiplying them together, if we get A times E plus B times G, we get A times F plus B times H. And then C times E plus D times G. Finally, C times F plus D times H. And then we transpose that, we interchange the rows and the columns. So then my first row is going to be AE plus BG. And then CE plus DG. And then my second row is going to be AF plus BH. And my next entry is going to be CF plus DH. And then the question is, are these the same? Well, do all the entries match? So is this entry the same as that entry? Yeah, because A, B, C, D, E, F, G, and H all represent numbers. And for numbers, order of multiplication and addition doesn't matter. E times A equals A times E, B times G equals G times B, and we add them together, we get the same result. Same deal here. EC plus GD certainly equals CE plus DG. Same deal here. AF plus BH definitely equals FA plus HB. Same deal over here. FC plus HD definitely equals CF plus DH. So we're good to go. These are the same. So it is interesting, I think, that when you take the transpose of a product, you actually end up interchanging the order of multiplication. You get the product of the transposes multiplied together, but in the opposite order. Right? A times B transpose is B transpose times A transpose, right? The order switches, which is kind of neat. I will point out, even though I don't think it really comes up, but I think it's kind of neat. It's also true for inverse matrices, which we'll talk about in a second here. But if you have A times B inverse, if it exists, it's equal to B inverse times A inverse, which is just kind of neat. Speaking of inverses, typically we only talk about 2x2 inverses, although again, I'll say the following. So for inverses, first and foremost, only square matrices get to have inverses. I should say, let me be more specific. Only square matrices can have inverses. But just like with real numbers, not every square matrix gets to have an inverse. So for real numbers, the inverse is pretty straightforward. Like, what's the inverse of 6? Let me be more specific. What's the multiplicative inverse of 6? I know I'm using words that might not be super like familiar with you, but just think about the inverse. What is the reciprocal or inverse of 6? Right. And it's called the multiplicative inverse because when you multiply 6 by 1/6, what do you get? Right, the multiplicative identity. I will also point out there is an additive inverse as well. The additive inverse of 6 is -6 because 6 plus -6 equals 0, the additive identity. Okay, can you think of a real number that doesn't have a multiplicative inverse? There's only one, and it's 0. Yeah, so I'll point out 0 doesn't have a multiplicative inverse. And don't you dare say infinity. Because infinity is not a real number. You can't multiply 0 by infinity and get 1. That's not true. You can, kind of, with limits, but you don't always get 1, right? So it's not an inverse. Well, matrices have a similar property that some matrices have a multiplicative inverse if they're square and meet another criteria. So here's the deal. For A equal to A, B, C, D, I'll point out that every matrix, square or not, has an additive inverse. You just literally take the negative of the whole thing, right? Negative A, negative B, negative C, negative D would be the additive inverse of this matrix. But A has an inverse. And when we say inverse, we always mean multiplicative. So if you mean additive, you say additive. Has an inverse if the determinant of A is not equal to 0. And the inverse is, you write it as A inverse, or A to the -1 power, but we say A inverse. It's equal to 1 divided by the determinant. I'll remind you that the determinant of A is equal to AD minus BC. So of course, we have to divide. So since we have to divide by the determinant, it better not be 0. And then here's the way I always think of it. Interchange the diagonal entries. So A and D switch places. And the off diagonals change signs. So whatever B was, you have the negative of that there. Whatever C was, you have the negative of that there. That's your inverse matrix. So for example, A is equal to the matrix 2, 3, 5, 7. Then A inverse is equal to 1 over 2 times 7 minus 3 times 5 times, switch the 7 and the 2, change the signs of the 3 and the 5. I do like, so depending on how this works out, I do like to simplify this. Let's see, this is 14 minus 15 is -1. So we really have -1 times this. Let's just distribute the -1. If it was like a 1/2, I probably wouldn't distribute it. But if it's a nice integer number, I usually like to distribute it. So distributing the -1 to the matrix, I get -7, +3, +5, -2. Let's check. In fact, let's actually, so when I say let's check, what do I even mean? Well, inverse matrices should multiply to the multiplicative identity, aka the identity matrix. So it should be true that A multiplied by A inverse, which is 2, 3, 5, 7, multiplied by -7, 3, 5, -2. Let's see, what do we get? We get -14 plus 15, which is 1. We get 6 plus -6, which is 0. We get -35 plus 35, which is 0. And we get 15 minus 14, which is 1. The identity. So inverse matrices should always multiply to the identity matrix. You don't have to check that, but it is something that's true. And we definitely use that later on. Oh, I think in this quarter, actually, that inverse matrices multiply to the identity because there's like a whole calculation of the thing that's kind of neat. Yeah, okay. So more to say about that? Not a whole lot more about that. There. Cool. Couple more, so just a couple more examples here. I want to get to that kind of this. So, do the following matrices have inverses? Let's see. So let's start with the first one. A equal to 7, 4, 2, 9. So if this was an exam question, I would point out it is not asking me to find the inverse. It is only asking me, does it have an inverse? And to have an inverse, what has to be true? It has to be square, and also the determinant is not 0. So let's find the determinant. Determinant of A is equal to 7 times 9 minus 4 times 2. If I was feeling really lazy, I would just write not equal 0, so yes. But here I'm going to actually calculate it. That's 63 minus 8, which is 55, which is not equal to 0. So yes, A inverse exists. And we could find it if we were asked to. I will point out that it would be 1 over 55 times the matrix where you switch the 9 and the 7, and you change the signs of the 4 and the 2. Again, not that we were asked to find it, I'm just doing extra work here. How about this matrix? B equal to 3, 6, 1, 2. Yay or nay? Definitely not. The determinant of B is 3 times 2 minus 6 times 1, which is equal to 0. So no, B inverse does not exist. It really is true. If there's no matrix that you can multiply this matrix by and get the identity matrix back. It's kind of annoying, but it's true. There are lots of square matrices that are not invertible. Also, this matrix, C equal to 1, 2, 3, 4, 5, 6. Definitely not. Not square. Yeah, let's do that. Yeah. So what to do with all this matrix stuff? Well, one of the things we're going to be doing a little bit this quarter and certainly a lot of next quarter is actually writing equations with matrices. Or I should say really systems of equations. So systems of equations. Most of the systems we're going to deal with next quarter, in fact, pretty much all of them, are systems of 2 equations and 2 unknowns. But in fact, let's start there. So let's say we have this following system. 2x plus y equal to 7, and x plus 3y equal to 4. This can be written as a matrix equation. Here's how it usually works. You want to write all of your variables and their coefficients on the left side. Everything is equal to on the right side. And you want to write the variables in the same order. So x is first, y is second, z is third, et cetera, et cetera, et cetera. So that then when you look at the left-hand side, you can just read the coefficients of x, y, whatever in order. So on the left-hand side here, I'm going to have the coefficient matrix 2, 1, 1, 3. The variable matrix x, y equal to whatever it's equal to, the matrix 7, 4. This matrix equation, which people often write as A times X equal to B. A is a matrix. X, we often think of a 2x1 matrix or a 3x1 matrix or a matrix that has only one column as a vector, right? We think of that, we call it often a vector instead of calling it a matrix. It's both. But this matrix equation is the matrix A times the vector X equals the vector B. And you can solve it by finding the inverse of A. So check this out. A inverse is equal to, let's see, 1 over 6 minus 1, the determinant. And then we interchange 2 and 3, change the signs of the ones. Which, again, normally I probably wouldn't, but I'm going to distribute that 1/5 and say it's 3/5, negative 1/5, negative 1/5, 2 over 5. And the way we can solve this equation is by multiplying both sides on the left by A inverse. It is important to note that we are multiplying on the left. So check this out. If I multiply both sides by A inverse, I have A inverse times A times X equal to A inverse times B. But A inverse times A, we just saw that whenever you multiply a matrix by its inverse, what do you get? You get the identity matrix of the appropriate size. And the identity matrix times any other matrix is just the other matrix. So this is I times X equal to A inverse times B. But the identity matrix times X is just whatever X is. So we end up getting here is our vector X, which is the entries X and Y, is equal to the inverse matrix 3/5, negative 1/5, negative 1/5, 2/5, multiplied by the vector B, which is 7, 4. And then if you actually multiply it out, you get, see, 7 times 3/5, which is 21/5, minus 1/5 times 4 is minus 4/5, so you get 21 minus 4, so 17/5. And then negative 7/5 plus 8/5 is positive 1/5. So the solution to the system is X equal to 17/5 and Y equal to 1/5. You could have solved this in a different way, right? Using a more typical approach of maybe isolating Y here and then plugging it in for Y there and solving for X and so on and so forth. But this is a process that works and also can be expanded to systems that have more equations and or more unknowns, where the process for solving it kind of manually becomes much more difficult. So that's kind of the idea there, is that we are using this idea to solve equations like this. And then it gets more complicated next quarter. So this idea of solving an equation like this by finding the inverse definitely is going to carry forward. Yeah, I don't want to sweat it too much right now. Let's see, is there anything else I need to say before we stop talking about this? Not really. Yeah, let's leave it there. As far as class on Thursday, I don't know. Trying to think what we should do on Thursday. Part of me feels like we should review because you have an exam on Monday. I guess that's what we should probably review. We'll review / try to encompass any material we haven't gotten to that's going to be covered on your midterm. So I'll take a look at that and see. And yeah.
System of the ratings will be on Monday too.
I don't know. Potentially. What's that? Yeah, I know. I was debating whether to try to start that today. And actually, good point. I do have a handout on Leslie matrices, which is another name for this topic. Somehow I didn't staple it, so let me make sure everyone gets both pages here. I will post this handout along with solutions on Canvas. I do think it's worth looking at, and I think it's pretty well done. But if you're not in class, I can certainly post both things on Canvas. But I would encourage you all to read through this and try to work on it. I think it's, I didn't write it, Grant wrote it, but it was pretty well done. So take the time to do it if you want to do like population. There is, I think on the last page, there are a few inverse things and we make it there. So Thursday, come prepared for anything.